In this video, we'll go a bit more into details of this theorem and find more details about the conditions in which this theorem is true or can be used. So the first thing we need to assume is that the pair of random variables x and y, they need to be continuous type. That means that the joint CDF f x y of x and y should be a continuous function in both x and y. Also, the function gxy and hxy, they should be continuous and differentiable. Otherwise, then you have to solve the problem with a bit more attention at those points which are not continuous or not differentiable, or these joint CDF is not continuous, then the theorem is not valid. So to see why, if you consider the probability that W is between small w and this W plus a delta W, and Z being bigger than real value Z, and Z plus a delta Z. Okay, so basically, if you consider this probability, that means that you are in a Z and then W, you're given a point with a coordinate of Z and W. So you consider a Z plus delta Z and W plus delta W. So probability that the random pair falls in this area. So so this probability is equal to this probability, and this guy, based on the definition of the joint PDF, is equal to this guy. Now, this means that you have these equations, these inequalities. So this inequality is the first inequality, this is the second inequality, this is the fourth inequality, and fifth inequality. So what we have to do is we have to draw four inequality in xy domain, and then you will have four curves. So the first curve, second curve, third curve, and fourth curve. So this is going to be in xy axis. So so you had at Z and W a differential rectangle of size delta Z and delta W. So this is there. Now the inverse of that here in xy plane is determined by four curves. This is the first inequality. So let's say this is gxy is equal to W. The second one is gx and y is equal to W plus delta W. And this guy is h of x and y is equal to I'm sorry, this is for Z, and this is Z, and this is equal to W, and then you have this one, W plus delta W is equal to h of x and y. So once you determine the boundary, so you have to integrate it. So because this rectangle is very teeny tiny, this sub area here also is teeny tiny. The smaller so this is the yellow area and this is the purple one. The smaller the purple, the smaller the yellow one, okay? So the probability of being in the purple one is exactly equal to the probability being in the yellow one, Okay. Sometimes if you have multiple solutions, you have multiple areas in XY. So you may have this one and this one. So if these points are mapped, these points are mapped into if these points are mapped into purple, this one is also mapped into here and here. So these are the set of the solutions. So we don't need to find these curves and these ones very rigorously. So you see that because these delta W, this delta Z, and so on, they will quickly disappear. So only thing that will remain is the ratio of these areas, which is the Jacobian. So the ratio of the areas, in the new domain, because you will have X, Y as the input, and then you have Z and W. So the ratio of the area at the output to the area at the input is determined by the Jacobian, and this guy is the Jacobian. So you calculate the partial derivatives. You have two outputs, two inputs, then you have two partial derivatives of the two outputs with respect to the two inputs. You get 4. So you have you form a matrix, and then you calculate its determinant, and then we call it the Jacobian. So this is denoted by Jacobian of GH with respect to XY. So you can, in your calculus, you have learned that this is equal to 1 divided by Jacobian of XY with respect to G and H. Okay, so and it is equal to inverse of the matrix if you calculate the derivatives with respect to derivatives of X and Y with respect to X, then you can easily show that. So basically, we have seen this one, and then if you have only one unique solution, so if G of X and Y equals Z, if the system of equation, and H of X and Y equal W. So if Z and W are known, and if you solve it, and you get only one unique solution, and the solution is X and Y, so X and Y is written in terms of Z and W, then your this is your final answer. So this is a summary of the theorem. If you have no solution, this guy is going to be 0. So if no solution, then we conclude that f of Z and W is going to be 0. So remember that this guy is written in terms of W and Z. So the right side, X and Y, shall be written in terms of Z and W. So this is the first step. So the first step is to solve the two set of two equations. So we must solve this one, find this one, and find the values of X and Y. So this is the step. So what are the values of X and Y which satisfy this set of equations? So this is the trick. So we must solve the following equation. So this is the first step. And then once we solve these two equations, we get the expressions for X and Y. So when you get this expression, you may get no solution at all. Then the joint PDF of the output is 0. If you get one solution, we have the expression, and so on. So we may get one solution, no solution, or multiple solution. In all case, this is true only for the case that you have one unique solution. If you have two solutions, then you have to add this value for the two solutions. If you have multiple solutions, you will have summation of the same function at all different possible solution. No solution, the summation of none is 0. So the second step is to take partial derivatives, determine the Jacobians, and evaluate the Jacobian, because this is written in terms of x and y. So you have to determine the value of these Jacobian at the solutions, at all the solutions separately, and then add this one. Okay. So so what we do, this is the general equation. So find the solutions. What you do, the solution, you determine a set of the solutions and then evaluate these functions at the solution. So this is much easier than the previous methods. So no care, no integration, and so on. So it's very, very quick. So you have to remember that x and y on the right side, all these x and y, so they have to be evaluated at all solutions in terms, and they shall be expressed in terms of only w and z, because this function is the joint PDF of w and z. So this is, there should be no trace of x and y here once you do this.